Now eventually stars run out of ways of generating energy by thermonuclear fusion. The final state of a star depends critically on their mass. We can summarize it with this figure. Here we have the main sequence stars. Red dwarf stars, we're going to see, are just going to kind of fade away and become white dwarfs. We'll talk about what a white dwarf is in a second. Ones about like our sun are going to go into their giant phase, and they're going to pulse for a little bit, and then they eventually go down and become white dwarfs. The massive stars become the supergiants, and eventually they're going to end in a supernova explosion. So start with medium mass stars. A medium mass star ends its life by ejecting a large fraction of itself back into space and forms something called a planetary nebula. Now, these have nothing to do with planets. The name comes because some of the first to be found in the 19th century looked a bit like images of Uranus. Now, a modern photograph shows a lot more detail. We have the remnant of the star in the center and this expanding ball of gas that's lit, and we can see it due to the UV radiation from the thing in the center. So that star in the center that's left behind is essentially the core of the red giant star that made the nebula. It is very small and very hot and is in a totally different part of the HR diagram. The central star of the planetary nebula is so hot it gives off lots of ultraviolet radiation that ionizes all the gas around it. The gas is then heated to about 10,000 degrees Kelvin by that ultraviolet radiation. And it has an emission line spectra. Eventually the gas drifts away from the star and becomes part of the interstellar medium, forming new stars. The central star of the planetary nebula has some very unusual properties. It's called a white dwarf. So how do we get white dwarfs? We have a low-mass star like the Sun. It's burning hydrogen. It expands into red giant as the hydrogen and then helium is used up. And the outer layers are driven off by this radiation pressure. The outer layers become a planetary nebula, which is just a shell of expanding gas that dissipates, leaving the core star. So with no fuel available for it to burn, the core star cools, becomes a white dwarf. White dwarf stars have masses like that of the Sun, but sizes like that of the Earth. The density of a white dwarf star is equivalent to 1 ton per teaspoon. Because it's so dense and so massive and so small, the surface gravity is about 100,000 times that of the Earth. It would take as much energy to climb 4 inches high on a solar mass white dwarf as it takes to climb from sea level to the top of Mount Everest on Earth. Now the matter in a white dwarf star is not like ordinary matter. It's not solids, liquids, or gases. In fact, there's no pressure in the normal sense. The star is held up by something called degeneracy pressure, which is something you can only understand from quantum mechanics. White dwarf stars are in hydrostatic equilibrium. Gravity is now balanced by electron degeneracy. Essentially, I can't get the electrons too close together. Degeneracy allows the white dwarfs to shrink with increasing mass. A white dwarf's mass cannot exceed a certain limit called the Chandrasekhar limit. If it does, it collapses. And the white dwarf's high density, about 1,000,000 grams per cubic centimeter, implies that atoms are separated by distances less than the normal radius of electron's orbit in an atom. The basis of degeneracy pressure is something called the exclusion principle. It's just a law of physics that limits the number of electrons that can occupy any given volume. Degeneracy pressure depends only on gas density, not temperature. When a degenerate gas is compressed, it heats up, but this temperature increase does not affect pressure. In other words, degenerate gases are less springy. Adding mass to a degenerate white dwarf makes it shrink and increases the gas pressure to offset the increased gravity. So again, a white dwarf, if I add mass, it doesn't get bigger, it actually shrinks. Continually adding mass will eventually make the white star collapse. The point of maximum mass for collapse is called the Chandrasekhar limit, and it's a value of 1.4 solar masses. All observations of white dwarf stars' masses appear to conform to the 1.4 solar mass limit or smaller. Now, white dwarfs can introduce a gravitational redshift in their spectra. Photons climbing out of the gravitational field must expend energy to do so. And photons can't change their speed, so it increases their wavelength. The amount of redshift depends on the white dwarf star's mass and radius. Knowing a white dwarf's radius from its luminosity and temperature, the gravitational redshift will give exactly the white dwarf's mass. Mass determination via the gravitational redshift provides a means to determine a white dwarf's mass in isolation. In other words, I don't have to have a binary pair to measure the mass of a white dwarf star. Now, but what if a white dwarf was in a binary system? There, a white dwarf may gravitationally capture gas expelled from its companion. Remember, any star has a solar wind, gives off material, and that material going in this direction is going to be sucked in and going to spiral down into the white dwarf. So hydrogen is compressed and heated on the surface of this white dwarf. That gas gets warmer and warmer and warmer, and eventually it reaches ignition. A fusion reaction in a degenerate gas results in an explosion, and we call that a nova. Novas can be visible to the eye and may occur repeatedly for the same white dwarf. That explosion does not destroy the white dwarf, as long as the white dwarf never exceeds the Chandrasekhar limit. And what about low-mass stars? Stars with a mass less than 0.4 solar masses are too small to ever ignite helium. When they die, they simply fade away as red dwarfs. When the nuclear reactions stop, the pressure inside decreases, they collapse and they become smaller. The collapse heats them up, so they quietly become white dwarfs in the same way the Sun will. They can have theoretical lifetimes, though, of 100 billion years. That's longer than the age of the universe. So we really can't see the results of any stars of this size reaching that age.